My name is Eric Scott, and this is my submission for Lab 5. So here's my RC circuit. This red wire is from digital pin 2. For the output pin, this black wire grounds it, and we have the current running through this red wire, through my resistor, then through this 10 microfarad capacitor, and then back into ground. And this white wire will measure the voltage across the capacitor into analog input pin A0. So if we take a look at the MATLAB simulation, we can see this thin line is a step input from 0 to 5 volts, such as the one that your output pin can create. The blue line is the response of an RC circuit with a 10 kilo ohm resistor, and this orange line is the response of an RC circuit with a 100 kilo ohm resistor. Both of these lines signify the voltage across the capacitor in that circuit. We can see the capacitor in the 10 kilo ohm circuit reaches this 5 volts a lot quicker than the capacitor in the 100 kilo ohm circuit. That's because the time constant for the 10 kilo ohm circuit is 10 times smaller than the other one. In my Arduino code, I have these two integers, Vout and Vin, that I'll use later. I set up the baud rate, and then I declare the digital pin 2 to be an output pin and write it to low for 5 seconds to completely discharge the voltage in the capacitor. In my loop function, I have two for loops. This first for loop writes digital pin 2 to high. It then records the voltage out of that pin and the voltage across the capacitor, and it prints these to the serial monitor. It then delays by 2 milliseconds, and this whole loop runs 500 times. This 2 milliseconds comes from the time constant divided by 50, and it runs 500 times to give us a period of 10 times the time constant. This other for loop is the exact same, except the pin is now outputting a low signal. So if we take a look at the processing code, we can see this integer A1 reads the voltage across the capacitor. Integer A2 reads the output voltage from your digital pin. It then multiplies both of these by 512 over 1024 to convert those numbers to voltages. These three blocks of code set up the numbers to split apart your graph into the 0, 1, 2, 3, 4, and 5 voltage lines. This block labels them with the respective voltage, and this block creates the legend at the top of your graph. So this block right here creates a circle for every data point from the voltage across the capacitor. The x value starts at 0 and increments by 2 every time. And our graph starts at 550 at the very bottom and subtracts the number A1 found earlier to find the y position. This block creates the same with the output voltage from your pin. And you can see your voltage across the capacitor is going to be a red circle, and your voltage from the output pin is going to be a green circle. And if we run that code, you can see the green line made of circles is the digital output pin incrementing between 0 and 5 volts. And the red line made up of circles is the response of the voltage across the capacitor. The graph looks the same using a 100 kilo ohm resistor, except the red line takes longer to reach 5 volts and 0 volts in between steps, and the sampling rate is also slower, so it moves across the screen slightly slower. So in my MATLAB data analysis code, all I did was divide the two arrays by 512, which was the total number of codes, then multiply it by the full scale range voltage of 5 volts. If we look at the graph, we can see for the 10 kilo ohm resistor, we have a period of 1 second, which is 10 times the time constant, which is what we expect, and it reaches the high and low points fairly quickly. And for the 100 kilo ohm resistor, we have a period of 10 seconds, which is 10 times the time constant of 1 second, and it takes a lot longer to reach the high and the low points, which is also expected.